All right, page 376 in your books, systems of inequalities. Hopefully this looks really familiar, hopefully. So they talk about in the business world, systems of inequalities are used to do like consumer surplus, supply and demand type things for those of you that are in. So the goal is that the supply and the demand have this equilibrium point, which is like the perfect little point. You'll see this change. You'll see this swing around depending on what's happening to one or the other. Here's the deal. Really, things are worth what someone's willing to pay it for it, right? I mean, that's how this works in a market. And so if they get too far above, we have too much supply, then my point where I can sell it changes, okay? And so they're always looking for this price point to be able to figure out what's the best price that I can get that's not going to reduce how much people buy. And then I don't want to go too far below that to where I could be making more money. I mean, that's really what businesses are looking at. Like, what's the best point where I can sell the most for the best price? So that's what this is going to be looking at for some of these things. How does that look? The first thing we're going to look at is just a system. This is actually not a linear system. This is just a system of inequalities. One of them is linear, one of them is not. So most of the ones we're going to be doing with our word problems are all going to be linear, right? But this is an example of one that is not linear. This is going to be used in sciences. I mean, if you're in physics, there's many, many physics problems that pick up a parabola type situation, and then you have a linear that cuts through it, which is what you're going to see here. So if you have something like this, you want to just graph the two equations, or inequalities rather, and shade it. So just think of it like in pre-cal world, in pre-advanced like algebra world. What would we do here? Well, we would graph it, and then we would see where they cross. So the first one, anytime I'm given an equation in standard form for these type of problems, I usually graph it in standard form. You can move it to slope-intercept, but just pay attention to your positives and negatives. So for example, if I were to do this one, my x-intercept is going to be -2. My y-intercept is going to be -2 divided by -1, so +2. This is a dashed or solid line. Y'all should remember that. Yeah, the first one is solid. The second one is dashed, right? So first one is solid. Second one is dashed. And then, of course, we have our shading. This says less than, but actually I'm going to shade it as a greater than. Why? Because I have a negative in front of this, and had I put it in slope-intercept form, my y would actually be greater than, because that negative in front of it would have flipped my sign, right? It would have flipped my sign. So this is actually going to be shaded above it because of that negative. If it were a positive in front of my y, I would shade below it because it's less than. But the negative tells me that were I to put this in slope-intercept form, I would have to flip it, okay? The second one is a parabola. You should recognize that, okay? So x squared is definitely parabola. Going up or going down? It's going down. Where's my vertex? So because this is outside of my function technically, my vertex is going to be at +4. So I have a parabola at +4 going down. You can see where this would cross the x-axis. Those are called my zeros of my function, right? So if I want to graph this perfectly and I want to see where my zeros are, I could just say, where would this guy equal 0, right? That's going to equal 0 at the square root of 2, which happens twice when a variable's involved. So it's going to happen at +2 and -2. So if I'm graphing this parabola, my vertex is here. I know my zeros happen here. And I also know that I have a dashed graph because it is just a less than. Now for this guy, the y is by itself, so I can shade exactly where the less than is, which is everything inside of my parabola. So it's all of this. So really I'm just looking for where they cross. They cross right here. So this is the region that's created there. That's what happens. Linears. So this is what you're going to see in your word problems. You're going to see systems of linear equations, which means it's not just going to be 1 or 2, sometimes 3, 4, like in this one. Very often your word problems will do y is greater than 0, x is greater than 0. Because it is trying to limit you to the first quadrant. Sometimes the word problems won't even tell you those limitations. They are logical limitations. So you have to look for logics and you have to look for what your linears are. This is just setting up solving one of these. So this is not a word problem, but this is what your word problems are going to eventually look like. You're going to set up your own linears and then you're going to graph them, right? And so for this one, we would just graph it. X equals a number. That's going to be a vertical line, right? So this guy right here is going to be a vertical line at -3, right? So I go to -3, solid line. You don't have to shade as you go. So you can do this line. We can do my Y line, which is a horizontal line at -1. All of those are solid. I think all of these, yeah, all of these are solid. We can do our other line. Also solid, and we can figure out the shading at the end. Typically, but not always, your shading will be enclosed. It's not necessarily enclosed. It doesn't have to be. And then we'll do my last line here. All right. So now we need to figure out where it's shaded. So those are my lines. And then I'm going to go to my shading. So for this one, it was greater. So it's this side of that line. It's on the above the green line. It is below this line right here. And it is below this line right here, right? So we have below this line and above this line. So this one flips. So we're actually going to get this little wedge right here. That's my answer. So you just have to shade in your answer. Below one, above one, and above the other two, vertical and horizontal. There we go. So this says, if a maximum or a minimum value of an objective function in a linear programming problem occurs, it occurs at one or more of the vertices of a feasible region. This tells you how long that it's been really something that they've started looking at from the 1940s, 46. So I find it interesting that they did optimization to improve supply programs for the Pentagon, which is where our defense obviously is, right? So I think that's interesting. So how does this help us? You can maximize and minimize these functions with this process. So if you'll recall, you'll have an objective function. Objective function. If it is like this, they'll just hand it to you. Here is your objective function that I want you to do whatever with, in this case, minimize. And then they will give you constraints. Constraints you can think of just like what the word means, limitations, okay? And so it's a supply limitation, it's a demand limitation, it's some type of limitation that you have on whatever you're trying to do, okay? So you're gonna create a region based on those limitations. You set that objective guy to the side at first. You do your feasible region, and that vertex theorem says, if you are trying to maximize or minimize a region, if you have a maxima, a point, it's going to happen at a vertex. So you don't have to test all the points inside your region because your objective function will be maximized or minimized at a vertex. That's when that's going to happen. So just figure out your vertices and then you can go from there. One of the ways to figure out your vertices is to graph it, okay? There's other ways to figure out your vertices. You can use your other methods, right? Solving by elimination, etc. But graphing the feasible region is one of them. So like I had said before, one of the things that they often do is a stipulation like this that keeps it all positive, for example. So they're telling us that x is greater than 0. Really, all they're telling us is that x is always positive. So you will be in the first and second quadrant here. That's what it's telling you. Y is between 1 and 4. That's another fun one. Y is between 1 and 4. That's always one that tends to throw people off, but it's actually kind of easy. It's just two vertical lines. So if it's between 1 and 4, you are going to draw a vertical line at each of... I just did those backwards, didn't I? Yeah. Who's helping me out here, people? Sorry. All right.
I saw another
So here's my x. There we go. So it's 2 horizontal lines for my y. I'm glad I at least caught it. There we go. All right, so we have a horizontal line at 1. We have a horizontal line at 4. Okay, so we're kind of boxing ourselves in here a little bit. We are to the right of the x-axis, and we are in between those. So we know we're somewhere here. Now we have 2 lines that we're going to graph. The first one's in slope-intercept form. You just leave it. That's fine. -1, and then up 1 over 2. And sometimes you want to walk that to see exactly where it crosses those, because that's going to help find your vertex. So I would actually keep walking this guy up so that I can see where it crosses. So -1 with a slope of 1/2, and you can see I walked it to see exactly where it crosses here, and then I kept walking to see exactly where it crossed there. That's going to help me when I figure out my vertex. All right, and so we're going to graph that line there. And then we're going to graph our last one. This is actually by, I would graph this with intercepts here, because it's just positive and -8. So here and here, positive and -8. I mean, +8 for both of them, not negative. Both of them are +8s. So we have this little region. You cannot assume, by the way, that it is the enclosed region. Sometimes when you minimize, it is not enclosed. It doesn't have to be enclosed. So we're going to double check it and see what region they're talking about. All right. So we know that we are on this side of the yellow and in between the red, right? And then we need to look at these lines. For my blue line, it's greater than, right? So it's above my group blue line. So I still have 2 regions that it could be here. And then for my yellow line, for my green line, that's this one right here, it's below that green line. So it's going to be on this side. So if it's above the blue and below the green and in between the red, it's going to be this little arrow looking shape right here, right? So I have, move out the way, guy. I have this little guy right here. That's what's going to happen. Okay? For this one, I probably don't have to do it algebraically. The vertices are nice and easy and pretty to see. So this is saying what gives me a max? Well, I'm just going to check my vertex. Only of my feasible region, though. So I say that because every year I get people that will indeed give me this as the maximum. That's outside of the feasible region. Or they're going to say, this is your minimum. No, because it's outside of my feasible region. So you're only checking these guys that make up your feasible region. However many sides you have is how many vertices you should have. Think about your logic from geometry, okay? Makes sense? So if you have a 1, 2, 3, 4, 5 sided figure, you should have 1, 2, 3, 4, 5 vertices, okay? You're going to take those. So I have the point 0, 1. I have the point 0, was that 4, hopefully? I have the point 4, 1, and 4, 4. And I have the point 5, 2. All right. So you want to take all of these points and you want to plug them into this guy and see what's going to give you your maximum and your minimum. They want both, okay? And so then you're just plugging it in. 5 times x plus 2 times y equals what? 5 times x plus 2 times y. 5 times x plus 2 times y. Right, so we're going to do this all the way and see what our max and min are. So this is what? 2, 8, 22, 28, and 29. So our maximum happens. So here's how you want to write this, all right? Your minimum is 2, and it happens at the point 0, 1. That's not a pretty at. Your max is, oh, that's 6, 2. Did I write 5, 2? Isn't that 6? 6, 2. There we go. 5 times 6. Yeah, so this should have been 5 times 6. That's 34. The reason you want to do this is when you get to word problems, If I say, what's the maximum profit? You want to tell me it's the maximum profit is this, and it happens when you make this many of these two things. So you have to know what your X and Y is, how you're labeling it. And so they're not going to hand you the objective function. You have to read your problem and figure out what your objective is. Write a system of inequalities, modeling the constraints, graph the feasible region, substitute your coordinates of your vertex into your objective function that you have, and then figure out what's your min or max depending on what you're trying to do. So look at example 4. Gaming Incorporated manufactures the vintage X and Y not play gaming consoles. Thank you for my variables. The company budgets $150,000 for labor and $600,000 for components. The components cost $100 for each vintage X and $150 for each Y not play. Labor costs are $40 for the vintage, $30 for the Y not. If the profit is $45 for the vintage and $60 for the Y not, how many should be made to maximize profit? What is the maximum profit? Okay. What are we trying to maximize? Profit. So that means profit is my objective equation. All right. So when you're reading all of this, you want to first figure out what is the point. All right. Why am I doing this? I am maximizing profit. All right. So then you have to say, what are my variables? They probably won't actually have variables normally in the name. So, but my variables are going to be my vintage X and my Y not. So granted, in this case, they gave you X's and Y's, but you want to label those. I promise you'll confuse yourself if you don't, okay? And you'll definitely confuse me if I can't figure it out. So you want to label what stands for what. All right. And then I immediately do my objective function so that I know those are not part of my constraints. So the profit, if profit is my objective, I'm going to read profit. So 45 for my X and 60 for my Y. That is my profit equation, okay? So I don't need to use those anymore. I'm done with those. Now I'm going to look for what my limitations are. The first limitation they talk to is a budget. A budget is going to be a constraint. Ask your parents if a budget is a type of constraint. It's not a bad thing, but it is something that limits you, right? You can only spend so much. So budget's going to be a constraint. The maximum they want to spend in their budget is $150 for labor. So labor is one of the things I'm going to do. I have a labor constraint. So I should have some X and some Y that is within my budget for labor. So it says labor cost. I'm going to go back and look for this. Labor cost. It may be hidden, but here it is, 40X plus 30Y. If it is a budget, do I want to be above budget or below budget? Yeah, so that should be below or equal to, right, my budget for labor. Okay. I have another limitation, 600,000 for components. So I have a components limitation, 100X, 150Y. And once again, since it's a budget, it is below. All right. Once you're done, make sure you have read through everything. They sometimes give you extra information that is unnecessary, but make sure you've accounted for all the limitations they've given you. It's just a good idea. The other thing I would say is if you want to do it, like say you want to divide out 10 here or something, just make sure that you put that back in when you answer the question, right? So you don't want to have an answer that should be like 50 and 60 and you give me 5 and 6, right? Does everybody understand what I'm saying? Like, I could make this 4, 3, and 1,500, 15,000, whatever. That's fine. Or you can just label your things larger, whatever you want to do. It doesn't matter. Just make sure that if you take out a 10 or 100 to get it smaller, that you account for it when you give me your answer. Okay. So you're graphing these. When you do these, obviously, if you use it in tens or whatever, you're going to have to do big numbers. Okay. There's a natural limitation. What is it? What's your natural limitation here? It's on my screen. Yeah, it's first quadrant, which a lot of them will be. So first quadrant is a natural limitation. So you're just going to graph these. I usually graph these by my intercepts. So like if I were to look at my first one to see what my intercepts are, then I would say, well, I would just say 150,000 divided by 4, right? And that's going to be my x-intercept there. So I would do like x-intercept, right? And I would calculate that. That's my method because I don't want to graph like slope intercept when it's like this. You're going to have a crazy slope intercept if you try to do it. Graph by intercepts. Y-intercept is going to be the same thing, just divided by the 30, right? So you're going to get what? 3750, 5,000. So if I were to do this in thousands, we would do something like here to here, right? And we're going to graph that line. And then we'll do the same thing for the second one. Do your intercepts. This guy is going to create a quadrilateral. So do your y-intercept and x-intercept here. You're going to get 6,000 for x-intercept, 4,000 for y-intercept, and you're going to graph that. So something like this. Now, here's the thing. You are probably going to have to use some other method to figure him out. Okay? You're in thousands right now. So this is where you're probably going to use some method to calculate this. You have lots of methods in your little tool belt here. You can certainly, when you're doing this, you can certainly divide that out, make them smaller. Multiply this guy by what, 5, -5. Do elimination to solve for that exact XY point. You want to be exact. So when you solve it, we're not going to take time because y'all should all know how to solve by elimination. You're going to get this guy. So now I have this right here is one of my points. This is one of my points. And this is one of my points. Logically, which one is not going to maximize my profit out of those 4? What's not going to maximize my profit out of those 4? Probably him, right? 0, 0. You don't even have to test him if you're maximizing profit. Don't bother, right? Test the other guys. So by test, I mean plug in 0, 4,000, plug in 1,500, 3,000, plug in 3,750, 0, and see which one maximizes it. It actually ends up being this one right here. So your answer would look like this. You would say max profit is, and what happens when you plug it in? You get a big profit here. Plug it in, get your 247,500. And it happens at 1,500 vintage and 3,000, why not? Okay, so you want to actually tell me, this is what your answer should look like, what your max profit is, and what you did to get it. Questions? Good, try one. Even the most carefully crafted models using the most accurate data cannot answer ethical questions raised when making business decisions. While mathematicians may help determine whether something can be done, biblical principles should be applied to determine whether it should be done. That's a really good statement, by the way. There are times when you can prove business-wise it's a good idea to do something, but it's not morally or ethically a good idea to do something, right? Just because you can do it doesn't mean you should. And so, this is why we have certain laws about price gouging, because you could charge certain things and get the money when people are in desperate need of it. But ethically, should you? No, you should not. And so this is what this is saying here, that you also have to, primary principle is your biblical principles should help you decide what you should do, even when you're talking about business world, especially when you're talking about the business world.